Since we just had a little refresher on force length velocity, I wanted to start out with questions from the exam that were difficult for many people that were in the category of force length velocity type questions. Broadly, the three categories of questions that seemed to cause people difficulty were, number one, and by far the most common, these force length velocity questions. And the second most common one was probably moment arm related questions. The third most common one was physiological cross-sectional area and strength. So let's start with this biggest category of force length velocity questions. Now, these are numbered, but of course, because the exam presented them in a random order, that this may or may not be the order in which you saw them. But nevertheless, we'll start with this one. This question says, suppose you're trying to ride a single-speed bicycle, which has no selectable gears up a very steep hill. Many of you have likely had this experience. It's quite difficult to do that, and the question is asking why, from a muscle mechanics perspective, why is it difficult? So what I'm going to do for this and for the remaining questions is I'm going to walk you through my strategy that I use for multiple choice questions like this. I think this will be useful for you if you take any of the standardized PT or OT or National Strength and Conditioning type exams in the future, because those are also multiple choice. So I'm going to go through each of the options, and then I'm going to mark whether or not I think this is a reasonable choice. And if it's reasonable, maybe I'll put a little squiggle next to it, and if it's not, then we'll put an X next to it. So this one, why would riding a single-speed bicycle up a very steep hill be difficult? Your muscle fibers are moving at a very small velocity, so they're producing very little power. Okay, that maybe seems reasonable because riding the bike up the hill and you can't go into a lower gear to spin around faster. So this part seems correct. And then I also know that when a muscle's velocity is very small, its power is very close to zero, because if you remember, there's that curve of muscle power as a function of contraction velocity, and it kind of looks like this, where this was that question that almost everybody got correct, which was at about 30% of the maximum shortening velocity, which is out here, the power of a muscle is maximized. So if you're say down here moving really slowly, it seems like your power would be pretty small. So that first option seems reasonable. Now, how about this one? Your muscle fibers are being stretched to a longer length than if the bike had selectable gears. Now, this is a little bit tricky, but if you think about it, would the kinematics, meaning would the joint angles that your knee and your ankle and your hip go through, would those change if the gearing of the bike changed? They probably wouldn't, because they're still going around the same circle, right? It's not like when you shift gears, the pedals change length or anything. So I'm going to say that's probably not a reasonable answer. This one, the slow contractile velocity limits the influx of calcium ions into your sarcomeres. Well, no, I don't think that's correct either, because we didn't learn anything about contractile velocity being related to calcium ions in the sarcoplasmic reticulum. Finally, the moment arms of your quadriceps muscles are smaller than they would be. Well, this gets back to the same idea about changing gears on a bicycle not affecting the range of motion of your joints. So it probably wouldn't change if your joints are going through the same angles. It wouldn't change the moment arm either. So in this case, I think this is the best answer. I think the most common incorrect answer was this one. Although this is, to be fair, this was quite tricky, because both this and this had this nuanced point about thinking about whether or not changing gears on a bicycle is going to change the kinematics. So this might be one of the ones that I curve. This next one is also related to the force velocity curve. And this one is saying that, again, maybe experience you've had before, when you're doing a heavy lift, you get stuck at the bottom of a lift, like a bench press or a squat. And the question is asking you to explain which of the properties of muscle maybe explains this phenomenon best. So how about this first one? Muscles are stronger in eccentric contraction than concentric contraction. Well, that's true, right? We just saw that down here. So eccentric, stronger here than here. So that seems reasonable. Maybe put a squiggle next to that as a possible correct answer. Stretch shortening allows for more concentric force production after an eccentric contraction. That's actually a reasonable answer also, which maybe I should put a note here to curve this one as well. And I think what I maybe should have done for this question is emphasize that if you were moving slowly for the lift. So this one also seems like a reasonable answer as well. Heavy lifts have a very slow velocity, which limits force production. Well, no, actually, it's having a low velocity helps with force production, because if the velocity is too high, then you can't produce very much force. And then this one is also a bit of a misdirection. We didn't really learn anything about changing the direction of force production having anything to do with calcium. So I'll definitely have to curve this one, because I think both of these, even though I don't think we actually talked too much in this class about stretch shortening, because I'm going to talk about that in Unit 4, I do think either of these are reasonable, so I will definitely curve this one. How about this one? This is a pretty straightforward question about what happens when a muscle fiber has a contraction velocity of 0. So when a muscle fiber has a contraction velocity of 0, does it produce no power? Yes, actually, it does, because there's two ways of thinking about it. One is that power equals the force times the velocity. So if the velocity is 0, no matter what the force is, power is going to be 0. Another way of thinking about it is with that graph we just drew earlier, which is the power as a function of velocity, and it looks like this. And the maximum power muscle can produce is at about 33% of Vmax, which is out here. So another way of thinking about it is when a contraction velocity is 0, right there, power is also 0. Okay, so that first option seems reasonable. Does it produce no force? Well, probably not, because isometric contractions have a velocity of 0, and that certainly produces force, right? How about this one? This is a little tricky, but it is at its minimum shortening velocity. Well, technically no, because you can go negative, although that's maybe another subtle, potentially arguable, curvable point. In that, remember, down here, we can actually get negative contraction velocities. That's what an eccentric contraction is. And then this last one, it is at its optimal fiber length. Well, not necessarily, because you could be doing an isometric muscle contraction in a very stretched out position of your muscles, right? So maybe if you're doing bicep curls and your arm is all the way out like this, but you're just barely holding the weight up by applying a muscle force this way, and it's isometric, so there's no velocity, you might not be at your optimal fiber length, but you could have a contraction velocity of 0. So we'll say certainly this one seems to be the best answer, although you could have maybe made a case for this one, despite that subtlety of actually being able to have negative contraction velocities. Okay, about halfway through this stack of force length velocity questions. This is a more applied one. You're treating a patient with cerebral palsy who complains of excessive calf muscle tightness when he's standing. Orthopedist has measured the patient's soleus muscle fiber length at 1.4 times the optimal fiber length. So that means on that force length curve, I just kind of draw a sketch of it where here's 1. That means we're up here at 1.4. So I'm already thinking active force production for this person is going to be really low. Clinical examination confirms that when standing, the patient has an abnormally high total force. A colleague suggests using Botox, which dramatically reduces muscle activation. Would this treatment reduce tension? Well, okay, this is a reasonable answer. It would scale down the active force length curve. this does not seem like a reasonable answer because the muscle activation doesn't change the optimal fiber length. And how about this one? Reducing activation scale down the passive force length curve? Well, that's correct. Yeah, changing the muscle activation doesn't change the passive force length curve because it's passive. That seems reasonable. Does reducing muscle activation reduce force production when the muscle velocity is 0? No, I think that's not correct because it does. Reducing muscle activation does change force production. So again, we're going over the maybe potentially coverable ones here. I think this is probably the best answer because we're already at a really low point on the force length velocity curve, but inferring that the excessive calf muscle tightness was a result of the passive force being really high, which we might remember the passive force curve, which looks like this, starting at 1. If we're at 1.4, that probably means we're up here, so we have very high passive force, which that's maybe the clue for this one being the best answer. Oops, I mean this one being the best answer. Oops, I mean this one being the best answer. There we go. Although I think you could probably, despite muscle activation being low during standing, you could make some reasonable case for this. So I will also put a curve down that one. Okay, a shorter and hopefully more simple one. The maximum shortening velocity of a muscle is usually measured in optimal fiber lengths per second. So suppose you had a muscle whose optimal fiber length was 9 centimeters. You might express whatever its Vmax is as some, maybe it's for slow twitch muscles, it might be 3 times 9 centimeters per second. So what does this suggest about the behavior of muscles with very long optimal fiber lengths? So one way to think about this is 3 times 9 is what, 27? And then maybe you imagine a muscle that has double that optimal fiber length. So if it was 3 times, I don't know, 18 centimeters per second, that would be some bigger number of, what, 54? So this one, I'm already thinking that the maximum shortening velocity should be really high for a muscle with a really long optimal fiber length. And so this seems already like a pretty good answer, but I don't think this one makes sense because if we're measuring it in optimal length fiber lengths per second and that goes up, then the velocity should go up. And then this one also doesn't really make sense based on that same line of arguing. So I would say this one is probably the best answer here. Okay, just 3 more questions to go in this category. So muscles with a long stretchy tendon like the Achilles can remain close to their optimal fiber length during running and jumping. This is true, by the way. Relying instead on the tendon stretching to change the length of the entire musculotendon unit, which is the muscle plus tendon. Why might this be advantageous? Okay. How about this first option? And by the way, the reason you might have already noticed we're going to likely end up with the first option being correct here because for many of these questions, that's because I just marked that as this is not necessarily the order you saw the answers in because they're randomly shuffled. So if the muscle stays close to its optimal fiber length, you will need a lower activation to achieve a given force. That's actually true. So if, let's say your force length curve looks like this, and let's suppose the maximum isometric force production capability of this muscle is 100 pounds. And you only want to produce 50 pounds. Well, if you're at the optimal fiber length, you can do that by just activating this muscle at 50%. Whereas if you were, say, out here at some longer fiber length, that gave you a max force production capability, say, of 75 pounds, you'd need to activate that muscle at what, 66% activation? You'd need a higher activation to get that same 50 pounds of force. So this seems reasonable. Can we eliminate these other options? If the muscle stays close to its optimal fiber length, it will nearly always be an eccentric contraction. Well, I don't think that's correct, because you can certainly be in isometric contraction, and you can also be in concentric contraction at any fiber length. How about this one? Stretching the tendon allows for more myosin heads to bind to actin fibers. Well, I wouldn't say that for two reasons. Number one, the tendon stretch tendons don't have actin and myosin in them, so that doesn't really make sense. And even if you played this forward in your head of what would happen to the muscle fiber, it would stretch out, and so then you'd get less actin myosin binding. So that one doesn't make sense either. This one, stretching the tendon changes the muscle's length but not its volume. Okay, well, it is true that muscles change length but not volume, but that does not actually have anything to do with its force production capabilities. So I would say that one is not a good answer either, leaving us with this one being the best choice. This second to last question, this is a graphical question. So we've got a graph here of the normalized fiber length of a muscle as a function of hip flexion angle. So this is looking at the psoas muscle, which, as you may be aware, is a hip flexor. So if maybe I draw a simplified rib cage and a pelvis like this, and a femur and a lower leg and a foot, the psoas goes something like this. I think one of them, it's either the iliac or the ilius or ilium or the psoas, actually goes up to the lower back. But right now we're looking at just hip flexion angle. So what happens when you, say, flex your hip out here? What happens to the length of this muscle? So as the hip is moved from extension, which is negative angles down here, to flexion, positive angles up here, this muscle length changes. That would make sense, right? As you flex the hip, you could see how this muscle would get shorter. And indeed, we move from, say, this 1.25 down to 0.7 from, say, here to here. So clearly this muscle is getting shorter. That makes sense. One of the things that people often worry about with this muscle is if you sit a lot, you spend a long time with the muscle very short, and then it gets tight. So this question is just asking, what hip angle would we expect the force production capability of this muscle to be maximized? So given that we're looking at force production and a fiber length, my mind is immediately going to muscle force length properties. So again, let's just either draw our curve, or this would have been useful to have. This is why this would have been useful to have on the exam. Go look at the force length curve. So what muscle length from muscle fiber length produces the most force? Well, it's actually pretty easy. It's the optimal fiber length, right? 1.0 times the optimal fiber length. That's the definition of the optimal fiber length, in fact. So all we need to do for this question is figure out what angle is the closest to gives us the fiber length that's closest to 1. So here's 1, and a little hint here, this is expressed relative to that optimal fiber length. So I'm going to go right to here. Whatever that point is, it looks like it's about 30 degrees. I don't even have to do process of elimination. I just know this is the right answer. One more force length velocity question down here. If a muscle is fully activated, and this is tricky because we got to think about activation, length, and velocity here, what's going to happen to the force production? A muscle's fully activated, okay. It is at 1.3 times its optimal fiber length. So what does that look like in the force length curve? 1 is right here. So 1.3 is going to be down here somewhere. Less force than the optimal force, maximum isometric force. And its contraction velocity at 0.7 times maximum shortening velocity. Now, okay, I'll draw this the way it's depicted down on the plot I showed you. This is eccentric. This is concentric. Here's isometric, and this is force production as a function of velocity. And we have Vmax out here. I think I drew this the same way. Let me double check. Yes, I did. I'm drawing the force velocity curve right here. So the question said we're at 0.7 times Vmax, so we're down here. Or on the graph that I just drew, we're down here. So both of these factors are contributing to reducing the muscle force production, right? Because the fibers are too long, so the force they can produce is down here. It's not up here, it's down here. And the velocity is bigger than 0. Now, let's say, since both of these are working to reduce, we should probably say this is the correct answer. Now, to be fair, I maybe should have specified this was a concentric contraction. You maybe could have inferred that, but to be more clear, I probably should have said this is a concentric contraction, as opposed, because if these were working in opposite directions, like if it was an eccentric contraction that was maybe negative 0.7 times Vmax, it would be unclear. You wouldn't have enough information. So I'll probably curve this one as well, even though I think if we assume it's a concentric contraction, which is a reasonable thing to do, given that I gave you a positive shortening velocity, this would be the best answer. So again, we saw a few here that maybe I could have done a better job at wording to make more clear. So again, I apologize for that. I will adjust the exam curve accordingly. But hopefully this gives you some better intuitions on how to analyze force length and force velocity questions.